Hello and welcome to Algebra 2 with Mr. Clausen. Today I want to talk about real-world applications of parabolas. So what I want to do today is just go over a few examples of how parabolic graphs or quadratic equations could be related to a real-world type example. And so with that said, I have three specific examples that I want to go through. And without further ado, I'm going to get started here. So the first example that I want to talk about here is a model for a company's revenue being represented by this quadratic function. Now, whenever we're looking at a function like this, granted this is being simulated by some context here, but it is a given situation where the a value of this quadratic function is less than 0. So it tells us that the parabola is downward facing. And so generally, we are going to have control of a few different things. So the independent variable, or the x variable, that we would normally see as, is going to dictate what we have control over as a industry. So what we normally associate as the x value is p in this case. P is the independent variable, which is clearly indicated as the price that we have of a good. And price, you know, if you own a company, you can control the price at which you set something. And then the y value typically associated here is actually r in this case, and this is your dependent variable. And this represents your revenue. And so a big thing that we're trying to do here is that where P is the price in dollars of a company's product, what price will maximize the revenue, find the maximum revenue. And so what we're going to do here is we're going to look at how do we find this point. And in this given context, what we're going to want to know is what is the vertex of this given quadratic equation or this given parabola, because the vertex is going to represent the maximum point of this given parabola. So the first thing that you have to do in a given example like this is that if you are able to get this situation is determine what your a, b, and your c terms are. Well, your a term is negative 15. That told us that the parabola is downward facing. The b term is 300 and the c term is 12,000. All right? And that might not be particularly useful at this point, but the a and the b are, because the axis of symmetry is always going to pass through the vertex or the maximum point of this quadratic equation, since it is a negative a termed quadratic. And so what I'm going to do is I'm going to find the axis of symmetry here. I'm going to go x is equal to negative 300 all over 2 times negative 15. And again, this is just fitting into the negative b over 2a format. And this is going to equal negative 300 all over negative 30. So if we set x equal to $10, then what we can assume is that this is the x value of our vertex. And it is going to be the point in which the revenue is maximized. All right, so we just answered the very first part of this question, and we're just using our knowledge of parabolas or quadratic functions in order to take advantage of this. And a lot of times with these examples, we're trying to keep them relatively simple. So most of the time what's going to happen is you're going to be looking for something like a y-intercept or a vertex. That's going to be your most common scenario in this given type of instance. And so we know what the x value of the vertex is. So if finding the maximum revenue is a goal here, well, we're going to plug in the price at which the vertex occurs. So we're going to plug in 10 for p and see what we get for r. So if we have r here, we can go and simply say negative 15 times 10 squared plus 300 times 10 plus 12,000. And very quickly see here that we would get negative 1,500. This is probably some cost. This is the price paid. This is the price acquired for each unit, plus some fixed source of income. And with this, we'll have 15,000 minus 1,500. So we'll get $13,500 of revenue from this given circumstance. And that's how we would answer the first problem. Now, the second problem I want to take a look at here is the equation for the model of a projectile fired straight up at an initial velocity of 64 feet per second is h equals 64t minus 16t squared, where h is the height in feet and t is the time in seconds. Find the time the projectile needs to reach its highest point and how high it will go. So we're just looking at a pretty specific situation here where, someone takes a, firearm of sorts. I don't know what it may be. Let's just say it looks something like this. And they shoot this projectile straight up into the air, and then it comes straight back down. All right, and then in this given case, we need to figure out, what the maximum height is. And so again, what we're going to be looking for is that vertex point, because the vertex is going to give us a couple things: the x value of the vertex and the y value of the vertex, or in this given case, the t and the h, is that at the t of the vertex, that'll tell us the time needed to reach the highest point, and the h will tell you what the highest point is. All right, so we want to find this vertex. And so with some of the information here, I'll point out that this equation is not in the standard function notation here. So the first thing I'm going to do is I'm just going to rearrange it here and say h is equal to negative 16t squared plus 64t with no c term. So a is equal to negative 16, b is equal to 64, c is equal to 0. And I can very quickly find that t as a variable, which is really our x, is equal to negative 64 all over 2 times negative 16. Do a little math. Negative 64 over negative 32. So t is equal to 2 seconds. So at 2 seconds, we'll reach the time at which the bullet or the projectile is at its highest point. All right, so we answered the first part of the question here. And so now we need to find out how high it actually goes. So we're going to now take this original equation, and I'm just going to plug in 2 for t. And so we'll go 2 times 64 minus 16 times 2 squared. Find 128. 4 times 16 is 64. And so the highest point is 64 feet. And so with that said, we can find that vertex of 2 seconds at 64 feet. And this is your vertex, which is the point that describes the answer for this given real-world example. So hopefully you're seeing a little bit of a trend here that really with the parabolic function, the main points of interest are going to be things like x-intercepts, y-intercepts, and vertexes. And really anything else is not necessarily useless, but in terms of many of these real-world examples, unless you have a very specific point you're looking for, are probably going to be less often used. I'm not going to say less useful, but less often used. And so now I want to look at one other example here, and I want to look at a real-world example that involves manufacturing. So again, the equation for the cost in dollars of producing automobile tires is C is equal to 0.000015x squared minus 0.03x plus 35, where x is the number of tires produced, and find the number of tires that minimizes the cost. What is the cost for the number of tires? All right. And so what I'm going to see here is that my A term is positive. And so this is going to be an upward opening parabola. Minimized cost is going to be at the vertex. So again, find that axis of symmetry. All right. Hopefully I'm not programming you too much, but again, it's a useful point to know in most of these circumstances. If you're modeling a quadratic function, chances are you're trying to find a minimum or maximum point in order to optimize something in some way, shape, or form. And so let's do this again where we set x is equal to, well, we got to figure out our a, b, and c terms. So a is equal to 0.000015, b is equal to 0 or negative 0.03, and c is equal to 35. So our axis of symmetry is that x equals negative 0.03 all over 0.000015, and we need to multiply that number by 2. And so what we'll quickly find is that x is equal to 1,000. And so this is the number of tires going to be produced, and this is going to be the number of tires produced that minimizes cost. And that's something I will probably ask you on a quiz or an exam, is to, go and find these values. Obviously, I'm telling you to go look at a vertex specifically, but it's going to be the number of tires that one should produce or I should say one should make, to minimize your cost. All right. And so we want to be able to go and describe what something means when we have a modeled equation. And typically I'm going to ask you to do this with a relatively simple and predictable model like this. So if we know that was the cost for that number of tires, well, we can go and plug that in now and take a look at it. So let's plug in 1,000 for x, and find that if we go and we plug this in, we can figure out pretty quickly with a calculator. Oh, we're going to go subtract that. 0.3 times 1,000 plus 35. Do a little math and find that making 1,000 tires will minimize the cost and create a situation where you only have a cost of $20. And so this is the cost if you make 1,000 tires. So with that said, I hope that you got a nice idea from this video of how to analyze some basic real-world examples, and that you got what you need in order to analyze those. Keep in mind that you're a lot of times looking for that axis of symmetry. You have to be able to do some rearrangement, some basic analysis. And with that said, let's do some math.